Okay, so we're going to talk about hydrolysis in this class. The word hydrolysis has actually many meanings in science. In this case, we'll refer hydrolysis as the dissolving of salt in water to produce acidic or basic solutions. So we're going to be talking about the pH of salt in water. Also, we'll talk about pH of various cations in water. And then finally, the pH of oxides in water. All right, so let's start with pH of salt. Salt is a class of compounds. If you're ionic and you can dissolve, you're a salt. Okay, you call it an SATP. If you dissolve, you will dissociate into your ions. Like, for example, sodium chloride solid will dissociate to sodium plus and chloride minus. Another example, potassium sulfate. If you drop that in water, it dissolves into potassium ions and sulfate ions. So here's my question. What is the pH of a salt? Okay. Does anyone want to answer that question? Anyone take a guess? If you're to guess, what is the pH of a salt? Acidic, basic, or neutral? Folks?
Acidic?
Why do you say acidic?
It was just a guess.
Oh, it's just a guess. Okay, that's fair. Any other guesses aside from acidic?
Neutral?
Neutral? Okay, I can kind of see why you guessed that. No one wants to guess basic? Honestly, I expected a lot of people to say neutral. I was shocked at the first answer being acidic. Because in grade 10, right, you learn neutralization, acid plus base, you get salt and water. And the resulting solution is supposed to be a neutral solution. So if you have salt in it and you're still neutral, that would mean salts are neutral. It actually depends on the salt. So it could be acidic, it could be neutral, or it could be basic. So it could be basically any pH. It just depends on what kind of ions are released. So it's not true to say all salts are neutral. So we're going to learn the different types of salts. Okay, why some salts are neutral, some are acidic, some are basic. So let's start with the very simple one, the neutral salts. Now, if you have a neutral salt, it means that you dissolved and the ions that you produced are all spectator ions, okay, which means they don't react with water to make anything. Okay, if you're not reacting with water, you're obviously not making hydronium or hydroxide, so you're neutral. Who are the spectator ions? Well, if you have alkali metals, group 1 on the periodic table, they basically are always spectators. They are not reactive at all. They're satisfied with their electron configuration. They've lost an electron, and that's it. That's all they want. Okay, they're not interested in any further reaction, so they're spectators. They don't react with water. Alkaline earth metals, group 2, are also spectators, so expect nothing from those. What about the negatives? Well, if you are, get this, a conjugate base of a strong acid. Okay. Conjugate base of a strong acid means you're an acid, let's say HCl. You lost your hydrogen, so you've done your job as an acid. You donated a hydrogen. So to speak. You're a spectator. You're not interested in any reactions with water. You sit there floating around and that's it. Examples are in the right column, like HCl or HI or HNO3, the NO3 part. All of the things highlighted in blue are spectator negative ions because they are the conjugate base of a strong acid. If you have two spectator ions, the positive and the negative, both of which don't want to do anything in water, so you have a neutral salt. Okay, like salt, sodium chloride, the table salt that we refer to, that's neutral. What about basic salts? Because not all salts are going to be neutral. So hydrolysis, here's the definition now, is the reaction of an ion with water to produce acidic or basic solution by the production of hydronium or hydroxides. You break up salt, you either produce hydronium or hydroxide, that's hydrolysis. If you have a basic salt, then obviously you produced hydroxides. For example here, sodium acetate. Okay, solid. You dissolve that, you get sodium ions and acetate ions. That is supposed to be a basic solution. You may be thinking, wait, what? I don't see any hydroxide. How's that basic? Well, think of it like this. When you break them up, the sodium ion is a spectator, right? It is not interested in any reactions with water. So this would yield you nothing. Okay, sodium plus water, or sodium ion plus water, you get no reaction. Okay, fine, you're boring. What about acetate? Acetate can react with water. It is a weak base. Okay, it is able to accept a proton. You see that? If you accept a proton from water, you make acetic acid and hydroxide. Okay, acetate is the conjugate base of a weak acid, so you're a weak base. So you are able to react with water, and you do produce hydroxides. And because you produce hydroxide, we say that the salt solution is slightly basic because of this equilibrium between the conjugate base and the water. Okay, is that clear? So that's why that equilibrium I showed you on top is a basic solution. Here is a visual of this. You have a beaker of water, and I'm about to drop sodium acetate into the beaker. The purple ball stands for sodium. The rest of that blob of black and red balls, that is acetate. If you drop this in water, they will dissociate. That's what ionic compounds do. Once you dissociate, well, you have the separate ion. This is a one-way reaction. Okay? Unless, of course, you're at saturation, but you're not. So this is a one-way reaction. You break up into your ions, and that's it. And then the acetate will steal a hydrogen from water. Okay, this is an equilibrium reaction. You will produce acetic acid, CH3COOH, and hydroxide. And the presence of this hydroxide will make the entire solution basic. This is why this is a basic salt, because it produces hydroxide once you dissolve it. Okay, any questions? So let's do some math with this idea. So calculate the pH of 0.30 molar sodium nitrite solution, NaNO2. Okay, so first of all, you have to identify which ion will undergo hydrolysis. Okay, if you undergo hydrolysis, then we can investigate whether you're acidic or basic. So you have two possible ions. You can have sodium or nitrite. We already established that sodium does nothing. Okay, so completely useless in water. So no reaction here. Nitrite in water, it will take a hydrogen from the water to make HNO2. And as a result, you make hydroxide. So this is the ion that will undergo hydrolysis. So you write the equilibrium equation of this to produce hydroxide, and then you set up an ice table. What is the initial concentration of NO2? Well, just look back to the question. Sodium nitrite is 0.3. It's a 1-to-1 ratio, so NO2 will also be 0.3. You would, of course, have zero products because you didn't react yet. Change is just X, and equilibrium is I plus C, initial plus concentration. You've seen this many times. This should be very intuitive at this point. So you've set up your ice table. You have all the concentrations at equilibrium. It is time to calculate X. You can write the Kb expression of this. And because we know that NO2 behaves like a base. It produces hydroxide. It must be Kb, not Ka. What is the Kb of NO2? I don't know. The question doesn't tell me. So that's why you have a table. You whip out the table. You can't find Kb on the table, but you could find Ka of the conjugate acid. So Kw divided by Ka of HNO2 will get you the Kb of base version NO2. Okay, please make sure you remember this. You look on the table for HNO2. What is the Ka? Well, it happens to be 5.6 times 10 to the negative 4. Kw is a constant. You always know that. You plug it in, and Kb is 1.786 times 10 to the negative 11. Okay, so you found the Kb. Okay, you've set up the ice table. It is time to solve for x. You can solve for x by plugging everything in. Notice that now at this stage, it is exactly the same as what we learned last time, calculating the pH of weak acid, weak base. Because I'm lazy, I'm always going to assume that x is tiny. Because look, your Kb is 10 to the negative 11. You're pathetically small. If you divide by 10 to the negative 11, yeah, you're going to be bigger than 100. So you can justify your assumption. You can drop the x, and you can solve for x to be 2.315 times 10 to the negative 6. That is the concentration of hydroxide. Okay, make sure you know what x means. Just check on the ice table. Where is x, and well, what does it represent? It is hydroxide. Because you now know the concentration of hydroxide, well, then you can solve for the pH. Well, the pOH is negative log hydroxide. pH is 14 minus this. And you know the story. 14 plus log of hydroxide. Eventually, you would get 8.36. And this would be the pH of your salt solution, sodium nitrite. And we expected this to be a base because our predictions tell us that it will produce hydroxide. And the pH is 8.36, which makes sense. Do you guys follow how this works? You take a salt, you identify which one can do hydrolysis, you calculate the pH of that equation. Same thing for acidic salts. Okay, this occurs for acidic salts as well. Nothing is changing here. Acidic salts dissolve in water to produce hydronium ions, like this right here. Ammonium chloride, NH4Cl. You dissolve that in water, you break into its ions, you have ammonium and chloride. And I'm telling you, this is acidic. Okay, why is it acidic? Well, let's look. Ammonium is a weak acid. It has 4 hydrogens. It doesn't mind giving one away. So it will react with water, give a hydrogen to the water to make H3O like this. Okay, and this equilibrium will produce ammonia and H3O, which makes the whole thing acidic. What does the chlorine do? Does chlorine have anything to say? No. Chloride just stays there as a spectator, does not react with water, so no. Chloride remains neutral. So basically, you have a source of hydronium, you're acidic. Okay, that's what makes ammonium chloride an acidic salt. You can then, of course, calculate the pH of this using the same strategy. So here's the visual. That's ammonium chloride. The green ball is the chloride. The blue ball with the white ones, that's NH4. Drop that into water. They will separate, dissociate. You will make NH4 plus, and Cl minus. And then here's what happens. NH4 will give a proton to water to make H3O, and that will be equilibrium. Because this produces H3O, you have an acid. Okay, make sense, guys? Okay, example 2. Calculate the pH of 0.10 molar of NH4Cl. All right, I'll give you some time to work on this. It's exactly the same strategy as the previous example. In fact, this is easier. It's acid, so you know what the Ka is. I'll give you around, 2 to 3 minutes, and I'll take this up. All right, so you're supposed to calculate the pH of 1 molar NH4Cl. Okay, so which ion will undergo hydrolysis? Well, we've established that it's got to be the NH4 because the chloride is a spectator. Okay, so you set up the ice table. Initial concentration is 0.1, 0 for the product, X, and equilibrium. So it's 0.1 minus X, and then you have X and X. All right, so from here, you set up the Ka expression. You know what the Ka is. Just look on the table. Okay, it's 5.6 times 10 to the negative 10. Solve for X using the assumption, because I'm always going to assume for acid and base, because for acid and base, if you have a weak acid and a weak base, you're going to have a small Ka or Kb. So chances are this is going to work out. 0.1 divided by 10 to the negative 10. That is like a billion. So that is bigger than 100. So you justify the assumption, you drop the X, you rearrange, solve. So X is approximately 7.483 times 10 to the negative 6. And remember, this is H3O. This is hydronium ion concentration. Okay, and if you know what X is, you can easily find the pH using negative log. So negative log of the hydronium, which is X, you plug this into your calculator, and you have 5.13. So if you have 0.1 moles per liter of ammonium chloride, you would have a pH of 5.13, which is acidic as expected, because we know that NH4 is an acid, so of course it's going to have a low pH. All right, do we have any questions? All right. Now this gets a little bit more complicated. Hydrolysis of metal cations. Well, if you have a metal cation, like for example, the ones in the table, if you check out those ions and look on the right way, they all have a Ka. What does that mean? If you have a Ka, that is the acid ionization constant. That means you're an acid. Only acids have Ka. But what does it mean to be an acid? What do you have to do to be called an acid? Well, you have to donate a proton. Wait, hold up. You guys don't have hydrogens to donate. They don't have hydrogens. They're just a bare positive ion. So how can you conjure up a hydrogen to donate to be called an acid in order to get a Ka? All right. So here's what we're about to learn. If you have a metal cation that is very positive, okay, 1 plus is not very positive. 2 plus, kind of, depends. 3 plus, 4 plus for sure, okay? They are so positive, they will force water to produce a hydronium ion. All right? Let's say aluminum, iron, or tin, they all have very positive charges. They can produce H3O ions indirectly. They don't produce it themselves. They get others to help them. How exactly does that work? Well, look at this one. Let's say aluminum 3 plus, very, very positive. When it becomes surrounded by water molecules, because water molecule is highly polar, you have a very negative side in the oxygen and a very positive side. And because aluminum is positive, you will attract the negative oxygen. You will attract 6 water molecules to surround it in like a 3-dimensional crystal. Okay, this is an ion dipole interaction. You're not actually bonding, you're just attracted. And you will get this equilibrium. Aluminum 3 plus, the bare naked charge, plus 6 waters. And in equilibrium with an aluminum water complex, aluminum H2O 6. There are 6 waters. You don't change the charge, it's still 3 plus because the aluminum is still 3 plus. You see what I'm saying? So the aluminum basically finds some friends, if you will, or finds some minions to surround it. Okay, and then what? How would you make H3O from this? Well, because the aluminum is so positively charged, it is very attractive to the oxygen, right? And because the oxygen already has 2 bonds with hydrogen, if you want to be attracted to the aluminum, that kind of weakens the bond with the hydrogen a little bit, because oxygen is like, I have a better option here. Why am I staying with this hydrogen, right? So what really happens is the aluminum kind of seduces the oxygen to cheat on hydrogen. So, I'm a better option here. You could just cut ties with one of the hydrogen. And that actually happened. There are 6 water molecules, right? 5 of them managed to remain loyal. You know what? I'm good. But one water molecule will get rid of a hydrogen and try to make a bond with the aluminum. Okay? The aluminum was so attractive that the oxygen is willing to give up a hydrogen because, I'm going to get my second bond with the aluminum and not the hydrogen. So the hydrogen basically gets dumped and it is released from the complex. And that lonely hydrogen will find a water molecule to make a hydronium. If you check out the equation for this, aluminum H2O6, that's the complex there, 3+, right? Plus another water molecule. So what happens is one of the molecules from the complex ditches the hydrogen. So you have aluminum H2O5 on the right side. So 5 of them didn't do anything. One of them became OH because, you got rid of a hydrogen. And because you became an OH, you became 1-, and that cancels the 3+ into 2+. So that's why you have aluminum H2O5 and an OH with a 2+. You lost the hydrogen. And then that hydrogen got sad, found another friend, and water, H3O+ is formed. You indirectly produce H3O, which makes the solution acidic. Okay, does that make sense? I'm not expecting you to calculate anything with this, although it wouldn't be all too difficult. All you need is the Ka for that complex, but your table doesn't have it, so I'm not going to make you do it. But you have to understand why these positive ions are acidic. And you should be able to explain how is it that they're able to produce hydronium ions when they themselves don't have any hydrogens to donate. Okay, so basically they lure somebody else to do that for them. Okay, any questions? All right. Moving on to a salt without a spectator. So far, the salts that we looked at, one of the salt produced is a spectator ion, and the other salt is not. So whatever that salt is will determine whether it's acidic or basic or neutral. Now, what if you don't have a spectator? Okay, both sides have something to say. So NH4F. NH4F will dissolve into ammonium, which is not a spectator. It will react as an acid, and F, which reacts as a base. So ammonium will react with water to make ammonia and H3O. We talked about that already. F is a weak base. Okay, it is the conjugate base of a weak acid, HF. So therefore, it is able to take in protons. It will react with water by taking a proton from water, making HF, and then releasing OH. So question, who wins? Right? NH4 is like, I'm going to be an acid. F is like, oh no, I'm going to be a base. And they're in the same solution, so they're competing with each other. So who's the winner? So is the solution acidic, basic, or neutral? How do we decide that? Does anyone know? Anyone want to take a guess? No? Think about what makes a solution acidic or basic. A solution is acidic if H3O outnumbers OH. Right? If you have more H3O than OH, you're acidic. And if you have more OH than H3O, you're going to be basic. So it all depends on how much H3O and how much OH do you produce. It's like a competition to see who can beat the other. Whoever wins in producing a greater amount of H3O or OH will dictate the acidity or alkalinity of the solutions. And what can tell you that? The Ka and the Kb. Okay, Ka is the ionization constant for the acid. If you have a large Ka, that tells you you will produce a lot of H3O. Similarly, if you have a large Kb, you will produce a lot of OH. Okay, so you compare the Ka of the acid with the Kb of the base, and whoever is bigger will be the winner, and they will dominate the solution, and they dictate the pH. Okay, does that make sense? You have to do a calculation to compare the K and the Kb of the acid and the base here. So the Ka of NH4, you can look on the table, 5.6 times 10 to the negative 10. What about the Kb of F? There is no Kb table, but you do need the Ka table. Find the Ka of HF, the conjugate acid. Okay, 6.3 times 10 to the negative 4. You divide that from Kw, you would get the Kb of F, and if you actually put that in the calculator, you get 1.6 times 10 to the negative 11. Let's compare. Ka is 10 to the negative 10, and Kb is 10 to the negative 11, and because Ka is bigger, NH4F will produce an acidic solution. Does that make sense? If both of your salts will interact with water, it's a matter of who does it better. Okay, if the acid does it more effectively with a higher Ka, you're acidic. If the base does it more effectively with a higher Kb, you're basic. Here's another situation where you can have an ambiguity here. If you're amphoteric, it means you can be acid or base. Okay, then what do? So consider this: sodium bicarbonate, NaHCO3. You put that in water, you have sodium ion and HCO3 bicarbonate ion. Sodium does nothing, okay? We wouldn't have to worry about that. But the bicarbonate ion, it has an H. That means it is able to donate that hydrogen to water to make H3O, and you will become CO3 minus, because that's the acid hydrolysis. But also, you have a negative charge, which means you're missing a positive charge. So a proton is a positive charge. You're able to accept the protons as the base. So HCO3 can then take a proton from water to make H2CO3 and OH. So both are possible. Which one is it though? How do you determine whether you're acidic or basic if you're amphoteric? Anyone want to answer this one? Based on what I said about the previous one.
You compare the Ka and the Kb again?
Yes, exactly. You compare the Ka and the Kb again. You compare the Ka of HCO3 to the Kb of HCO3 and see who's bigger. Right? If you decide to be an acid and a base, well, you got to be better at one than the other, right? Like Michael Jordan plays basketball and baseball. What do we know Michael Jordan as? A basketball player. Nobody ever talks about his baseball career because he sucked at it. But he was like the greatest of all time in basketball. So he's a basketball player. Here, you got to be better at one than the other. Okay? You're either good at being an acid or you're good at being a base. Which one is it? So compare the Ka and the Kb. You're going to have to calculate this. Okay, Ka of HCO3. Look on the table, 4.7 times 10 to the negative 11. That's the Ka. Just look. Well, the Kb, you have to calculate from the Ka of the conjugate acid. Okay? It has to be the Ka of H2CO3. If you use the Ka of HCO3, you make a mistake. You will get the wrong answer. So make sure that you use the Ka of the conjugate acid. So, if you look on the table, the Ka of carbonic acid, H2CO3, is 4.5 times 10 to the negative 7. You divide that from Kw, you get 2.2 times 10 to the negative 8. Okay, let's do a comparison. Ka is negative 11. Kb is negative 8. Oh, Kb wins. Okay, because negative 8 is bigger than negative 11. So that's why the bicarbonate ion produces a basic solution. Sodium bicarbonate is baking soda. The common sense tells us that this is a base. We know that because it's common knowledge. Why is it a base? Well, this is why. Because the bicarbonate ion, the Kb is higher than the Ka. Does that make sense, guys? When you have an amphoteric ion, you have to consider both situations. It could be an acid or a base. So which one is bigger, Ka or Kb? Then you will know. On a side note, the common mistake for these type of questions is that you divided the wrong Ka. I told you about this already, but I had a student before doing this question. Yeah, she made the mistake of finding the Kb using the Ka of the same thing. And she got, very coincidentally, she got the same number. So Ka equals to Kb for that question with her calculation. And she's like, wait, that means they're neutral. But I know for a fact this thing is not neutral. And then she got confused and she lost marks because she divided the wrong thing. So please make sure you don't apply the formula wrong. Okay, oxides. If you have oxides, you can either have metallic oxides or non-metallic oxides. This is like a review of grade 10. If you have a metallic oxide, you have a metal and oxygen. If you dissolve a metal and oxygen into water, you will produce hydroxide. So for example, calcium hydroxide. In water, you make calcium ions and OH molecules. Calcium ions are neutral, while OH molecule is basic. So metal oxides are all basic. Okay, non-metal oxide, like CO2, for example, they will dissolve to become acidic. Okay, here's why. CO2 plus water. Well, that makes carbonic acid. That's the thing in Coca-Cola. Carbonic acid will spontaneously break down and it will donate a proton to water to make the bicarbonate ion and H3O. You can, of course, cancel the carbonic acid on both sides. You can write the net equation. Carbon dioxide and water, a non-metallic oxide, will produce a bicarbonate ion with H3O+, which is an acidic solution. All right, so please know that metallic oxides are basic, non-metallic oxides are acidic. Right, that's just a rule of thumb that is true all the time. We good? So I just gave you a lot of information just now. Are you able to determine whether a salt is acidic, basic, or neutral using all that we've learned? All right, so I'll give you around 10 minutes to figure out whether these guys are acidic, basic, or neutral, and then we'll take it up together. If you make mistakes, learn from them. You're probably going to make some kind of mistake here because there's a mixture of everything. So go ahead and work on this, and I'll take this up. Okay, so the first one, potassium sulfate. Which one is it, acid, base, or neutral? Folks? Hello?
Is it basic?
Basic is correct. Why is it basic though? What made you think it was basic?
I don't know if that was right, but I was like, SO4 would gain a hydrogen. So I was like, okay, basic.
Yeah, that's basically the way to think about this, yes. Potassium, you know, is neutral. It's an alkaline metal. So that leaves sulfate. SO4 has a charge of 2-. So naturally, it will want to take in hydrogens, and it will be unable to donate a hydrogen because it just doesn't have one. If you're a proton acceptor, then you're basic. So this would be a slightly basic solution. See how this works, guys? Okay, iron 3 chloride. Which one is it?
Acidic.
Acidic, good. Why do you say it's acidic?
Because it is a metal cation.
Okay. So yeah, that's the tricky one. But iron 3 plus is one of the special metal cations that are very positive. They will form a complex with water, which will eventually release hydrogen. And chloride is a spectator. HCl is a strong acid, so chloride being the conjugate base of that strong acid will be a spectator. So overall, you have iron contributing to the acidity, chlorine doing nothing, so it's acidic. Lithium nitrate, anyone? That one is the easy one, lithium nitrate.
Is it basic?
How did you get basic? NO3, right?
Yeah,
Like
because
the
it's
first one. Right?
Wait, one at a time? Ivy, what were you going to say?
Because I think that it doesn't have a tendency to release hydrogen ion like a proton.
Oh, you don't have one, sure.
Yeah.
And anything to add? It's actually neutral. I know what you're thinking. Wait, hold up. NO3 minus. Right? Why can't that take a hydrogen? It's missing something, right? It has a minus. It's missing a positive charge. The reason for that is nitrate is the conjugate base of a strong acid. Nitric acid, HNO3, is a strong acid. It will 100% lose its hydrogen. That means there's no way it's taking one back. So that means you have to be a spectator. You don't have a hydrogen to release, and you won't take a hydrogen back. You don't do anything with water. So nitrates are always neutral. Lithium is an alkali, so you have neutral and neutral. This one is neutral. You see what I mean? Yeah, some of these are tricky because the conjugate base does look like it can take a hydrogen, but it won't because it is the conjugate base of a strong acid. So look out for those. NH4NO2 is a tough one because you need to do math in order to figure this out. Does anyone have the answer for this one? Wait, no one got here? You need to calculate the Ka of the NH4. Compare that to the Kb of NO2. You notice that this is NO2, not NO3. NO3 will be a spectator, but NO2 is a weak base. Because HNO2 is a weak acid, so that's why NO2 can be a weak base. You are able to take a proton. So you have an acid and a base. You compare, and I forget the numbers, but NH4 won. NH4 has a higher Ka than the Kb of NO2, so therefore it is acidic. Okay, the next two are fairly simple. MgO, anyone? Come on, guys. A grade 10 student can do that one. Basic, yeah, thank you. Magnesium oxide, a metal oxide. In grade 10, you learned that this is basic, and in grade 12, we learned why this is basic. Because water will break that up. Magnesium is a spectator. Oxygen will bond with water to make OH. Okay, so that makes it basic. NO2. Similar to the previous one. Nitrogen with an oxygen. Nitrogen is a non-metal.
Acidic.
that will be acidic. Okay. If metal oxides are basic, then non-metal oxides are acidic. This is why NO2 is such a deadly gas. If you breathe this in, it will irritate your lungs because you have water in your body. NO2 will react with the water in your body to make nitric acid inside of your lungs. And you can see that is a bad thing, so don't breathe this gas. That's acidic. All right, that one is a tough one. Sodium hydrogen phosphate. Anyone got this? Sodium is a spectator. Okay, you don't have to consider that. But hydrogen phosphate, though, that is amphoteric. You're able to donate hydrogen, but you're also able to accept hydrogen. You see? Because HPO4 is a 2 minus, you're able to take in more positive charges to become neutral. So yes, you can take hydrogen in. You have to compare the Ka of this to its Kb. And if you do that, you're going to realize the Kb is bigger, and so it's going to be basic. Okay, does that make sense, everybody? Caesium iodide. Anyone? That's an easy one. I don't think anyone got to the end because there wasn't enough time, I'm guessing.
Is it neutral because of the iodine?
Yes. Caesium is alkali. Oh, that goes without saying. It's neutral. Iodide is also neutral. Just remember, all the halogens except fluorine are neutral, right? Because they're all strong acids. HCl, HBr, HI, they're all strong acids. So iodide will not do anything in water. Okay, last one is quite difficult. What is it? Calcium we can rule out, that is neutral. HSO4. First of all, is that amphoteric? Can it be an acid and a base?
Yes.
Yes. Okay. It does look like it can it? It has a hydrogen. You could just donate that hydrogen. Okay, cool. You can be an acid. And also, you're missing a hydrogen, right? Because it should be H2SO4, but you only have one hydrogen, so you could, of course, take one back. But no, not really. This is not amphoteric. It looks like it is. It can donate a hydrogen, no problem, but it cannot take one back because H2SO4, sulfuric acid, is a strong acid. This is the conjugate base of a strong acid, which is not really a base. It does not take the hydrogen back. So tricky. This is just like nitrate, same story. It looks like it can take a hydrogen back, but you have to be careful. If you're a conjugate base of a strong acid, you won't take it back. So you're unable to get a proton. You can only donate a proton. So this is actually acidic. In a way, sulfuric acid, a strong acid, after it reacts, the conjugate base is not a base. It's actually another acid. It's a weak acid. You see, yeah, that's one of the few weird ones you have to be really careful of. If on the test, if I ask you, which of the following is amphoteric, be careful. Is it the conjugate base of a strong acid? If it is not amphoteric. So I hope you have a better idea of how to determine whether a salt is acidic, basic, or neutral. You have to consider the ions, whether it will react with water or not. Does that make sense, everyone? All right, I'm going to summarize the whole thing. You can have many different types of situations here. The first row deals with the very easy ones, the cations from a strong base, and the anion from a strong acid. So of course that's going to be neutral because they're going to be spectators. A strong base, well, you probably have an alkali metal with an OH or an alkaline earth metal with an OH, both of which will not react with water. Okay, they're spectators. And the anion for strong acid, that's the conjugate base of a strong acid, like a nitrate, a chloride, a sulfate, a hydrogen sulfate. those will not hydrolyze. So the pH is 7. A cation from a strong base, well, they're not going to do anything. With an anion from a weak base, so in the second row, if you have an anion from a weak acid, if you have a weak acid, the anion, the conjugate base, will be a weak base. So yes, you will react with water. The positive ion won't, but the negative ion will. And because it is a weak base, you will make the solution basic. pH will be greater than 7. Okay? If you have a weak base, the cation from a weak base, compared to the anion from a strong acid, its conjugate base won't do anything, so that's neutral. But the cation from a weak base is a weak acid, so that will make the solution acidic. Okay, and if they're both weak, then they can both react with water. Then you have to compare the Ka with the Kb to decide who is the winner. And finally, if you have a really positive metal, excluding row 1, group 1 and group 2, alkali and alkaline earth metals don't have this property. It's just the transition metals and the metals on the right side of the periodic table. If you have a really high charge, then you're an acid. Okay, does that make sense, folks? That will be it for this class. Okay, so we learned salt solutions. How do you determine whether it's acidic, basic, or neutral? We learned how to calculate the pH of various salt solutions. We also learned about positive cations and how they can become an acid, as well as metal oxides and non-metal oxides. Okay, so that covers hydrolysis. Different situations, it depends on what you have. Do we have any questions? Okay, I'm going to end this.